the H double bonded to a alcohol, and it says it is insoluble in H2O, and I don't understand why, because I'm pretty sure when it's 1 through 4, it should be able to be soluble.
No, that's the one. It was not 1 through 4. There were 45 carbons in that one.
Yeah.
Because I thought the same thing. I was like,
Were there
1 through 4.
parentheses around it?
Yeah, there's parentheses and 45 after.
Yeah.
Only because I did the exact same thing.
Yeah.
I have the quiz, I think. Yeah, I did literally the exact same thing. I was like, 1 through 4, I know this.
Right,
And then
okay.
he was like, 45, and I was like, yep, I know that too.
Okay, yeah. So if you see any parentheses, just be wary of that. So anytime it's...
So I definitely need 6 and 7. Chapter 6 and 7.
Thank you.
She's closing the blinds because it's blinding.
She's trying.
Blinding us.
Is it good?
Yeah.
Basic? Oh, it's all
It,
right.
it stays
Oh,
down.
careful. Jeez, why? I probably could have reached that without me doing that. Too much liability. So I have a feeling did it look something like this?
Yeah.
Okay,
Exactly.
yeah. So anytime you have parentheses, that's an indicator that there's more than one carbon that looks like this. Okay. So, all right. So just be wary of that.
Yep, I did the exact same thing.
So that wasn't polar?
It
No.
was not water soluble because it had
soluble.
it was like 45 carbons.
Gotcha. Okay.
Yeah.
I don't know about everyone else, but like chapter 6 and 7,
Yes.
I definitely need.
Is that the SN1 or something?
Oh yeah.
Yeah.
Oh,
Yeah.
oh my.
I'm like, I just need to revisit that 17.
Okay,
I didn't
absolutely.
even memorize that. Sorry.
Exactly. Like I need to.
So I do want to talk about that chart a little bit. Just because E2, if in the chapter it goes into a little bit more detail, and you find that there's a little bit more going on than just what the chart states. So in a previous one, I had kind of shown an updated chart. So I just want to, I'll draw that one. So it's not exactly the same as Dr. Cosper's one. I made a few edits.
Wait, what chapter are we on?
6 and 7.
6 and 7.
Oh my god.
What?
Oh shit.
Yeah,
You guys are
need to
usually
tone
so
it down.
friendly.
It's finals.
She might be recording for the YouTube video, right?
I am recording for YouTube videos.
Sorry to outsiders.
For anyone listening now.
They don't see your face.
It's YouTube. There's much worse things on YouTube.
Wait, so do they not? Oh, do they see the board?
Yeah, they don't see
Yeah.
us. They see
Oh.
who they
I'd be-
Thank goodness.
I don't know, I'd rather be seen on it than like recorded. I don't like my voice.
I never knew how masculine my voice was until I heard it recorded.
I never knew how high pitched my voice was until I heard it recorded.
Just like that we all look stressed.
Yeah, we're all done.
That's not what yeast is. So like yeast?
I have an allergy dog at work that I have to do catches and do allergy grounds, so it's just
I don't know if I could do ice cream with
because once they figure out which protein you're allergic to, like if it's to a food allergy, it's more it's not worth it. Like they're gonna be allergic.
Okay. So essentially, I've kept the chart pretty much the same. You'll just notice that I've added an extra row here, and E2 is actually found in 2 different places. So the chart that Dr. Cosper and I believe even Dr. Fred has kind of used some of it, just shows E2 as being primary alkyl halides, big bulky nucleophiles. Now that can happen, but that's one very small instance of when an E2 reaction will take place. Typically, an E2 reaction is going to take place with actually secondary or tertiary alkyl halides and a big bulky nucleophile. So the chart that Dr. Cosper has isn't incorrect. It just doesn't give you the full picture. And based off of some questions, previous questions from exams, I just didn't want there to be any type of confusion. So E2, you're actually going to expect that to happen with secondary or tertiary. There's only one instance when you have a very strong basic nucleophile that it's going to occur with a primary. I know that seems confusing, but most of the time, like, I can't put a percentage to it, but most of the time, secondary or tertiary with a big bulky is going to be E2. Alkyl halides only happen when you have something that's very strong, a very strong base. But we're going to we'll go through all of these. Again, it's usually helpful to at least have a good idea of what this chart is. If you understand each component of this chart and why the components are the way they are, you should be able to answer any question on chapter 6 and 7, okay? So let's start with SN2. So what does SN2 stand for?
Substitution.
Nucleophilic?
Bimolecular.
Bimolecular, good. What does bimolecular mean? Two what?
Molecules required depends on like the concentration of two separate molecules. That's right.
So the rate of the reaction is affected by the concentration of two reactants. I'm going to say that again. So bimolecular is when the reaction rate is based off of the concentration of two reactants.
So, the reaction rate is dependent on the concentration
Of two reactants.
Reactants.
Yes. So in this case, we're talking about the concentration of the alkyl halide and the concentration of the nucleophile. So if you decrease your amount of nucleophile, the reaction rate is going to be reduced as well. So if you remove some of either of these, the reaction rate is going to go down. If you increase, the reaction rate is going to increase.
And the two reactants is the alkyl halide and the weak base, or the small?
The nucleophile.
The
Just-
nucleophile,
Yep,
okay.
yep.
Okay.
Okay, so SN2, we see that they prefer primary alkyl halides. Who remembers why?
Is it because the bond, it's got two weak bonds in the alkyl, like two pi bonds?
I'll tell you this. So when we're comparing primary versus tertiary, a lot of this has to do with where the reaction is trying to take place. And I wish I had my other roly one. I'll draw it over here, I guess. So we have our nucleophile. Okay, so here we have our primary alkyl halide, here we have our tertiary alkyl halide. So in a substitution, both SN1 or SN2, the reaction is taking place at the center carbon. So the nucleophile has to attack that center carbon in any substitution reaction. So if we have, if we are trying to get into this center carbon, it makes sense that it's going to go faster if there's not a lot of stuff in the way.
Oh yes.
So what is it called when you have a lot of big steric
hindrance.
hindrance? Okay, perfect. So alkyl halides reduce steric hindrance. Okay? The less bulky groups you have around that center carbon, the easier it is for the nucleophile to attack. Now, there's a specific kind of attack that happens in SN2. Does anybody remember?
A backside?
Backside attack. Very good.
It's okay.
Okay, so we have the nucleophile. It's attacking the carbon. Is this, how many steps is this reaction, an SN2 reaction? It's one. What's the term? So if we were to draw the transition state, right? Why have I drawn dotted lines between the nucleophile and the halogen and the carbon?
Bond's broken.
At the same time that bonds are formed. The term for that is? No.
Entropy.
Bonds broken minus bonds formed. When bonds are being broken and formed at the same time,
No, I don't.
I don't remember what it is.
concerted.
Oh.
Yeah, we just
Yeah.
it's us. It's really us.
what the definition of that is again?
So when bonds are being broken and formed at the same time, that means that the reaction is concerted.
I know this is gonna sound stupid, but is there like a way to remember that? Because for some reason I can never remember that word.
Okay. Does anybody have a fun way for remembering that one? I tend to have fun analogies, but I don't think I have one ready to go for concerted.
Okay. I can be dramatic and be like, don't be concerned, they're broken and formed at the same time.
I was going somewhere along the line of concert.
Or conceited.
Yeah, I think conceited.
They need both at the same time.
Yeah, they're just so they're so self-absorbed. The carbon just has to have both the nucleophile and the halogen.
Yeah.
Okay.
I like how my brain works.
So that's why there's almost looks like there's 5 connections
Exactly.
there, but there's obviously not.
Exactly.
Okay.
Yes. Yes. Question.
So if it's not concerted, it does not have a transition state?
Right. So if it's stepwise, which is what we have in unimolecular, you don't have a transition state. You have what's called a intermediate. There's a specific type of intermediate that we're going to talk about. What's used in unimolecular? What type of intermediate? What was that? Carbocation. Sorry for my small handwriting. All right, everybody good with that? Okay, so talked about alkyl halides. It's concerted. So we talked about how having fewer alkyl groups reduces steric hindrance. That's also the reason why we want a small nucleophile. So again, we're trying to attack that center carbon. If we have a big bulky nucleophile, it's more difficult to attack there. So we want a small nucleophile for the same reason. Reduces steric hindrance.
Could you define steric hindrance?
Yeah, sure. So when you have big bulky groups, it slows things down.
That's it.
That's what steric hindrance is. Yep. Okay.
Can you give me a piece of white paper? Because I just totally made my paper ugly. I'm going to redo this.
Okay, let's talk a little bit more about this portion here. What type of solvent do SN2 reactions prefer?
Polar aprotic.
Polar aprotic, very good. What does polar aprotic mean? Or what does aprotic mean?
I don't know.
No protons.
No protons, okay. Now, why don't we want protons in this type of reaction?
They get in the way, don't they?
How do they get in the way?
They would bond to the... It ties up the nucleophiles.
The nucleophile, exactly. So remember, nucleophiles have what charge?
Positive. Negative.
Negative. They like positive things, so
right.
they have to be negative.
Right.
Okay? What charge does a proton have?
Positive.
Negative, positive attraction. Okay? So we don't want a bunch of positive ions floating around to tie this up. Very good. Okay, let's see. What does the term stereospecific mean?
It's... I don't really know, but I want to try to like work it out that it's specific for the nucleus that it wants, for like the stereocenter.
Yeah, I think that's a good start to thinking about it. So it's where the reaction wants to take place. So if it's stereospecific, the reaction can only take place at one specific spot. So SN2 reactions can only be a backside attack. They can only occur at that area of the carbon. So that's why SN2 reactions are considered stereospecific.
I have a question.
Yeah.
Can you go back over like when you started talking about it being polar aprotic and why it needs to do that? Can you say that?
Absolutely, absolutely. So aprotic means that it doesn't give off protons. Protons, we know, are just H plus ions. It would be bad to have a bunch of H plus ions floating around because they would attract and tie up the negatively charged nucleophile. Okay? Now, taking another step back, we know that this is a bimolecular reaction. If the nucleophile is tied up, that means there's going to be less concentration of it, which means the reaction itself is going to run slower.
Okay.
Okay? We don't want anything that's going to react with and reduce the concentration of the nucleophile.
Thank you.
No problem. Okay, taking a step back to stereospecificity. Let's see. Wish I had a bigger whiteboard. Okay. I am going to get out of the way. Okay. So here I've just drawn our starting product, okay? And this is our final product, all right? Now, because it's a backside attack, the nucleophile is going to end up on this side of the carbon, so that's why I've drawn it that way, okay? Now, if I ask you to find the absolute configuration of this molecule, okay, who would be able to do that?
I don't even know what that means.
Okay, so absolute configuration goes is from chapter 5, where we talked about isomers.
Oh,
Okay, yeah.
I do know what that means. Okay.
Okay, so absolute configuration, you're going to look at the attachments to the carbon and prioritize them based off of atomic weight. Okay, so looking at these 4 attachments, which one would have the highest atomic weight?
The halogen.
Halogen. Even without knowing which halogen it is, right? Because the smallest halogen is fluorine, which is still larger than carbon. So be number 1. What would be the second highest priority?
The methyl.
Methane.
The methyl, yep. And then we've got 3 and 4, okay? So in any case, you start at 1, go to 2, keep going that way. So 1, 2, keep going around. So we've got a clockwise. Is that R or S? R, thank you. Okay? Absolute configuration of our final product.
Would be an S.
S, because the nucleophile, again, we don't know exactly which nucleophile, but you can assume it is going to be more than carbon. So 1, 2, S. So we went from R to S. That's going to happen every time you do an SN2 reaction. You're going to switch. So if you start with R, your product will be S. And if you start with S, your product will be R.
No matter what.
No matter what.
Okay.
For those of you that are following along in Dr. Cosper's notes, did I hit everything on this side? Did I forget anything?
Yeah, you're good.
Okay. Any questions on SN2? No. Okay. So we're going to move on to E2. Just keeping in mind that, yes, primary alkyl halides can react only when you have a strong base. Any other time, it's going to be a secondary or a tertiary alkyl halide running for E2. But a lot of this still applies. Okay? Now I'm really running out of room. Where are the rolly ones that used to be down here? The rolly whiteboards. I'm asking you, Audra, just because you're the only peer
I
tutor.
think upstairs.
I don't know why
I
they...
think people keep stealing them.
How dare they? Okay.
I don't know how. It's really difficult to move them.
I-
Some of
I-
them
I-
back there.
I didn't see it, but that's okay. We'll keep going. I'll just bear with me. Let's see. So E2. All right. Okay, so the main difference between these two has to do with where the attack is taking place. Okay, so if you remember from SN2, our nucleophile is doing a backside attack at the center carbon. Okay, that's why we needed a small nucleophile to get in there, right? Now, when we're looking at elimination reactions, you're picking off the periphery hydrogens. Okay, so the nucleophile is not worried about getting into that second center carbon. It's attacking one of the peripheral hydrogens. That is why we can have a big bulky nucleophile in this case, because we don't have to worry about attacking in here. So steric hindrance really isn't a concern at this point, which is also why we don't really have to worry about having multiple alkyl groups. Okay? If we're just attacking the outer hydrogens, we don't need to be small, we don't need to worry about steric hindrance. Okay? Let me see. This is still stereospecific, even though there are multiple hydrogens here. There's only going to be one hydrogen that's going to be attacked, and it's going to be kind of the one that's opposite the halogen. This is referred to as a topside attack. Oh, sorry.
No,
Oh,
not
oh.
you. I dropped all my stuff.
Oh no.
That was dramatic. I dropped 2 papers, but it's all fine.
Now are you drawing the dots again because it's concerted?
It is concerted. So I'm trying to color code it between bonds that are broken and bonds that are formed. So the black dotted lines are being formed. The brownish are being broken. So you're absolutely right. This is concerted. This does take place in one step. We have the nucleophile pulling off this peripheral hydrogen. That's going to cause a carbon-carbon double bond to form, and the halogen is going to be removed. So we have a carbon-carbon double bond. What's the final product? Alkene.
Why is the halogen being removed too?
So basically, the halogen falls off at the same. This is all happening at the same time.
Right.
Right. So when this gets pulled off, it makes this carbon look to make a bond in a sense, right? Because it's only bonded to 3 things.
Okay.
The only other thing that it can bond to is the carbon, and that would give this carbon too many bonds.
Okay.
I'm sure there's a much more scientific way of thinking of it because it's all happening at the same time.
Right.
But that's what you have to worry about. Okay? So essentially, removing this hydrogen is going to cause a cascade. That's the way I think of it.
Okay.
Okay? Any questions on the transition state? Okay? It's concerted, stereospecific, can only be a topside attack. Polar aprotic for the same reason as SN2. We don't want that nucleophile being tied up. It's still a bimolecular reaction. Ooh. Any questions with E2? Very similar to SN2? Okay. Okay. Unimolecular. What does unimolecular refer to?
Only one. The rate is only dependent on one
Exactly. What is it
Reactant.
dependent on? Which reactant?
nucleophile.
No.
No. Man.
Actually, the alkyl halide.
Okay.
Okay? So the concentration of the alkyl halide is what drives the reaction. The nucleophile, actually, the concentration doesn't cause any changes. Now that's a little weird to think about, just how these molecules work. Now, we already talked about the fact that this is a stepwise reaction. So the first step is the same for both unimolecular reactions. So we have our tertiary alkyl halide, and in the first step, the halogen comes off. It falls off. This creates our intermediate, which is a carbocation, which should tell you why we want tertiary alkyl halides. Why do we want tertiary alkyl halides versus primary?
Does it have to do with stereochemics again?
No, I wish, right?
I wish.
So, how about this? What's the most stable carbocation?
Tertiary.
Ding, ding, ding. So, if in our first step we're creating a carbocation, it would make sense that we want to start out with something that's going to make a stable carbocation. We start out with a primary alkyl halide. It's very unlikely that that carbocation is going to form because it's so unstable. Okay, we want something that's stable, so we want to start out with something that's going to give us something stable. Tertiary carbocation. Okay. Now, again, so the first step is the same for Sn1 and E1. It's just the halogen falling off, and that is the rate determining step. So that's another clue as to what is the driving force of this reaction. So depending on how fast that halogen falls off, that determines how fast the reaction goes. So the better your leaving group, the faster the reaction.
What determines a better leaving group? Just
So in Dr. Cosper's notes and in your lecture, you talk specifically about the best leaving group or the best halogen leaving group. Who remembers? Which one? No?
Fluorine.
Iodine.
Wait, but
yeah, right
it's
here.
Oh, the
Don't-
iodine
don't-
tripped me up because it's not the
Yeah.
most reactive.
Yep. So that's a little different. It's a little different.
Okay.
So iodine is the best leaving group for all of these.
And that's because it's larger.
It's larger, yes.
It's coming back to me.
It's all right. It was a long time ago.
So what's the bromine best for? It's
So bromine, yeah, it's the most selective while still reacting. Iodine is so selective that it doesn't even react.
Yeah, right.
Okay.
Well, it ties in.
All right, so SN1, our halogen has fallen off. We have our carbocation. This is where the nucleophile comes in. Okay, so our nucleophile is going to attack the carbocation, and it can actually attack either above or below. Okay, that's kind of that empty p orbital where that positive charge is kind of hanging out. So the nucleophile has two different options in where to attack. So would this reaction be considered stereospecific?
No.
No.
And it's specifically because it doesn't have a preference whether it attacks from the top or the bottom.
Right, there's more than one option.
Do you have this quiz?
which one?
Probably.
Chapter 6 and 7.
I got you. I have them all
Yeah,
here.
so that's how
Do you have a question from the quiz?
I do, but I kind of want to see if it's a little different. Like,
Okay, yeah, no problem.
if the quizzes.
So when we're looking at this SN1 reaction, there's two different places that the attack can take place. Essentially, the nucleophile 50% of the time is going to attack from the top, and 50% of the time it's going to attack from the bottom. So you get 50% of each of these isomers, okay? If you have equal amounts of stereoisomers in a solution, what do you create? Racemic mixture.
Equal amount.
I remember that from last class.
Equal amounts of two enantiomers. So if you look on Dr. Cosper's notes, just because for the sake of time, so you'll see two different products are formed, okay? Because 50% of the time, the nucleophile is attacking from the top. This is SN1, which I think is page 3, 4.
Yep.
So you're going to get 50% of your product from attacking in the top, 50% from attacking at the bottom. When you have 50% of enantiomers, you end up with a racemic mixture. Okay, so because you have equal amounts of those two products, you end up with a racemic mixture for an SN1 reaction. Okay.
And this ties into the R and S configuration because if it
There's
attacks
no
from the top, it would be.
Yeah. So technically you would have equal amounts of how it rotates light. So it's slightly different, but it does have to do with stereospecificity. So yeah.
And this happens because of two enantiomer.
Yeah. So your two. No, you got it. your two final products.
I'll make sure to bleep out all the bad words or something.
I don't know how to do that on this. Okay. I think the last thing we have to talk about is the type of solvent for SN1 reactions.
Protic.
Polar protic. Okay. So why do we not care anymore if there are protons floating around?
Oh, because it doesn't depend on the nucleophile.
Exactly. So before we were concerned with these hydrogen ions reacting with our negative nucleophile and slowing down the reaction. But these unimolecular reactions are only dependent on the concentration of your alkyl halide. So if we have some protons reacting with the nucleophile, it's not going to affect our overall reaction. Does that make sense? Okay. All right, so SN1, tertiary, because it makes the most stable carbocation. Small nucleophile because we're still trying to attack the center carbon. We're going to have two-step reaction, making a carbocation. Because unit can attack the top and the bottom, it's not stereospecific, and it prefers polar protic solvents because we don't care about the nucleophile being tied up. It also helps the carbocation, so that's another layer of that.
How does it help the carbocation?
So that's a great question. That's a Dr. Fred question. But I know in the book it talks about it helps form and it helps stabilize. But
Okay.
my knowledge hits a wall there. Any other questions on SN1? That is a great question. Okay, so E1. Okay, again, a lot of similar things happening. The very first step is identical. Okay, the halogen is removed, and we make our carbocation. So that's why we want tertiary. The big difference here is where we're attacking. Again, with elimination reactions, we're attacking the peripheral hydrogens. So that's why we don't worry about having a big bulky nucleophile. Okay, so we're not attacking the center carbon, we're trying to pick off one of these hydrogens here. Now I've drawn 3 arrows, so that means that all those hydrogens are up for grabs here. Okay, going back to why it's not stereospecific.
Whereas the SN2 and E2, it was because it was attacking the one opposite to the...
Exactly,
Okay.
it was a very specific topside attack, only one of those hydrogens was going to get pulled off. Or had the option to be pulled off, in a sense. Okay, so, okay. Nucleophile is going to pull off one of those hydrogens, leaving this carbon with only 3 bonds. That's going to drive a carbon-carbon double bond, making our alkene. All of this still applies for the same exact reasons. The only difference is the big bulky nucleophile because our point of attack has changed.
And then the other difference is that the halogen has already left, so the halogen doesn't just fall off like it
That
did
was the
when-
same for both of them. I just didn't draw
Okay.
it a second time. So that's the same for both. In Dr. Cosper's notes, she shows it. It's the identical first step.
Okay.
Okay? Any other questions?
Is it topside attack?
These don't have a specific type of attack because there's multiple.
Okay.
Okay?
Yeah.
So these are named because there's only one option.
Okay.
Okay?
Can I just take a picture?
Yeah, of course.
Like mine's
Yeah.
still
Are you sure you want to?
It's better than what I had.
Anything will help.
Jess, how long ago did you take this? If that's not weird to ask.
2012?
Why do you remember it?
I'm
Because
really
I've
proud of
tutored
you.
it every semester since then, even post-graduation.
Oh, okay.
So
You've been doing it?
I know I did not know this as well as you think I know it now when I was taking it. Okay. When you repeat it and you repeat it and you read the book and you read the notes and you read the book and you read the notes, it becomes more, it makes more sense. It's hard to get it all in one semester.
Yeah.
Are we good with 6 and 7?
I think so.
All right.
So let's just do it again on my own, and then I'll come back.
Yeah.
Are we just going up from here?
I know I had a lot of questions about, like, non-specific questions about chapter 14,
Chapter 14, okay.
because we didn't really have a quiz on that one to help
Right.
guide.
That's the last one, right? That's
Yeah.
delocalized pi systems.
Yeah, like I said, I don't have any specific questions, but maybe like a brief overview.
I will say that Dr. Cosper's notes, and I don't know if his notes mimic this, I feel like there's a lot of repetition in the notes. And so because it's 2 pages, I feel like it's more deceiving. So I want to take some time and just talk about the pi systems, because I think that's the main thing you need to know. And then everything else kind of goes along with that. Okay.
This is 14, right? Yeah.
Okay, so delocalized pi systems, electron delocalization, these are big scary terms, okay? Electron delocalization just means that electrons are moving.
Moving like off of the molecule or just
So
moving in general?
they're staying in the molecule, but they're moving from their initial bond. Okay, if you've ever heard of resonance structures, or if you have any familiarity with that, that's what they're referring to. So you can draw the bonds in multiple areas because the electrons are moving. They're not static in those bonds. I think the best example that everybody is semi-familiar with is this molecule here. What is this?
Benzene.
Benzene. Why do I have a circle in the middle?
It's just
Oh,
another way to
three.
draw it. There's 3
Because there's
bonds.
3 double bonds, but it's because they can move anywhere.
Exactly.
Oh,
Okay?
Then
So-
so makes sense now.
So this is one way to draw it, but I can also draw it like this. They're identical. And that's because the electrons in this double bond can also be here, but could also be here. Oh, wait, it's a circle. Okay?
But they're always like, you know,
They're,
opposite to
they're,
each other.
yeah, they're still in the molecule, and there is a pattern to it in a sense, but all this means is you just have electrons moving, and this really occurs because you have alternating double and single bonds. That's what this chapter is about. When you're talking about conjugated diets, all that means is you have double, single, double. And you can have double, single, double, single, double, single. Like you could have as many of those next to each other.
But they're always
Double,
alternating.
single, double, single, double, single. But as long as you have a single bond in between those two double bonds, electrons just love it. Okay, they can run around as much as they want.
Oh,
So as
that's
long
the
as there's
rest.
alternating double and single bonds.
Yep,
The electrons move within them.
it's like a roadway.
Is that like resonance?
So
Yeah,
it is
exactly.
resonance, so it is definitely the same concept.
Yes, so resonance is the stability that comes from electron delocalization.
Oh, I'm gonna.
Resonance is, can you repeat that real quick? Stability?
Resonance is the stability that comes from electron delocalization.
Thank you.
No problem. Okay, so essentially I've drawn 4 carbons bonded together, and I've just drawn the p orbitals. The p orbitals, that's the pathway that the electrons are moving through, okay? So essentially, you could draw it almost as if there's an electron in each one. But you could have the bond here and here, or it can move and be here and then have a negative charge here because we've gotten electrons moving. So there's just constant moving. You can think of the p orbitals as the road that these electrons can move on.
So they can move outside of the p orbitals.
Think of it as more through the p orbitals.
Ooh, okay.
Through? All right.
Wait, before you erase it over. So like,
Yeah.
let's just, from left to right, the carbons are 1, 2, 3, 4.
Sure.
So electron on carbon 1 could move to carbon 2, to carbon 3, to carbon 4, or 4 to 3 to 2 to 1.
But they're
Does-
following the road.
They're following the road.
Now can the top electron move to the bottom, or does it have to stay within?
So technically,
Or I guess they're
You
already
can-
moving
they're
that way
already- yeah,
anyways, so
yeah.
okay, that was stupid.
no, that's not stupid at all.
Yeah, a little.
It's a lot of self-abuse on this YouTube video.
I'm gonna have to make a lot of apologies after this. Okay, so some more terminology that's really all meaning the same thing. So we have something that's called an allelic system. I don't know if you use that term in class. That's just referring to a double bond next to a single bond. So here we have our allelic system. Now, we can form radicals from this, we can form cations from this, and we can form anions from this.
Can you say that again?
Yep. So from this system, allelic system, we can form radicals, cations, and anions.
From this one specific
Yep.
allelic system, like if it was a different one,
Or from
No,
allelic
from
systems.
the
Allelic system.
whenever you
in
have a
general.
double and a single bond next to each other. Oh, that's a good question.
Gotcha.
This is generalized to more than just this one specific
Well,
one.
this is a lot more simple than trying to figure out Cosper's notes.
Yeah.
That's a big compliment. All right, so let's start with radicals, even though it's essentially the same thing. So with all of these, the bond is breaking here. Doesn't have to be that specific hydrogen, but a carbon and a hydrogen are breaking.
On the carbon that's attached to a single bonded,
Yes.
single bonded carbon.
Yes. Okay. So depending on where the electrons go and the type of cleavage we have, that's how we get the different either radicals or ions. Okay. What type of cleavage happens to create radicals?
Bond cleavage? No.
Specific. Starts with an H.
Homolytic.
Homolytic, very good.
Oh.
I know, that's a
Right.
different chapter, but it all
Right.
comes back.
It's haunting me.
So, homolytic cleavage just refers to an electron going to each one. They're sharing it. Each one is receiving one electron. So, we can end up with it looking like this, or
Each element, so a carbon, hydrogen, each element, each an electron.
Kind of like reverting back to the original state.
okay? So, if the electron stays there, we have a radical here, okay? If the electrons are moving, we could also draw the radical here. Because we have electron delocalization, we can draw it in two different ways. So the resonance structure, you could see, would look like this. Oops. Okay, so this is kind of, this is the benzene ring with the circle in the middle. This is drawing the bonds one way, this is drawing them the other way. So this is just a way of representing it to show both forms, okay? So instead of having the double bond on one side or the other, it's showing that the double bond can form on either side,
So you're
okay?
gonna make us draw that?
No,
Thank you.
just kind of explaining, because there are a lot of diagrams here. You need to know that this can turn into radicals and different types of ions. And you
Radicals, cations, and anions.
Exactly.
Is an allelic system can form radicals, cations, or anions.
Yes, and through electron delocalization, those electrons or positive or negative charges can be shown on like different parts of the molecule. You don't have to draw it, but you have to understand that concept. Okay?
And then that one just shows like both of those structures kind of in one.
Exactly. And
Okay.
if you look at Dr. Cosper's notes, you can take this out and put a positive charge, and that's what the cations are going to look like. You can take this out and put a negative charge. And that's what, well, it's going to be a little bit different, but essentially the same thing.
And this is all because of electron delocalization.
Yes, so resonance structures, yep, electron delocalization. But you have this capability, okay? So allelic systems, radicals, cations, anions. Electron delocalization means that you can draw resonance forms to kind of incorporate that movement. Okay, now why are we talking about these systems? Why does it matter, okay?
Stability.
Absolutely. These are unusually stable. And it has to do with just the electron movement itself.
So not specifically the allelic system, but the localized.
Does the resonance make
The
it stable?
delocalized pi systems, and yes.
Oh,
So,
I understand resonance. It's been so long, I'm so sorry.
Stability, resonance, okay? So delocalized pi systems, okay, alternating double and single bonds, allow electron movement, which gives resonance, which makes things very, very stable. That one sentence covers like 75% of these notes.
Can we repeat that sentence?
Absolutely. So, delocalized pi system. So, alternating double and single bonds. Allow for electron movement or electron delocalization, which cause resonance, making very, very, very stable molecules.
What's after resonance?
Very, very stable. Resonance,
Which makes it stable.
yes, yep. Okay. I think I'll do some vocab, and then I just want to talk about Diels-Alder and kinetic versus thermodynamic control. I think that's the best way to kind of do chapter 14. What is the term for a molecule that has two alkene functional groups? Don't all answer at once.
This feels like something we should know. Oh yeah, that's
So-
definitely something we should know.
Wow.
If you see diene, you should be able to break up that word, okay? ENE referring to alkene, right?
Okay.
Di referring to two. So dienes have two carbon-carbon double bonds, okay? There's different types. Okay, so you can have two carbon-carbon bonds directly next to each other. Cumulene. Should know that word, cumulene. So two double bonds right next to each other. If you have alternating double, single, double, that's conjugated diene. Conjugated.
So would the top one be cumulene diene?
Yeah, or you
Okay.
could probably just say cumulenes because the "ene" is in there, but
Okay. But conjugated
diene. Yep.
if they're alternating.
Yep.
Now, do dienes, it could be like a chain of 45 carbons as long as there's only two double bonds and it's a diene?
Yes.
Okay.
This one is probably the most important because again, alternating double, single, delocalized pi systems, right?
Mm-hmm.
This one is just non-conjugated. So I have two single bonds in between the double bonds. Okay, so there's some separation. So the pi orbitals aren't as neatly lined up. Okay, so non-conjugated. You could also say isolated.
And that's just like the term for, is more than one single bond between the
In
double
between them,
bonds.
exactly, yep. Okay, all set with these? Not too bad. Okay. So the next piece is specifically talking about conjugated dienes. In fact, the whole second page is specifically about conjugated dienes because they're a type of delocalized pi system. So the first page is just about these. The second page is conjugated dienes. Okay, so if we have our conjugated diene, okay, these are considered very electron rich. Okay, which means they're easily attacked by electrophiles. Okay, so electrophiles are going to attack, making carbocations. I'll do my H's.
Can you say that sentence again?
I forgot what I said. Conjugated dienes are electron rich, which mean they attract electrophiles. And, oh, I just wrote E's instead of H's. Wow. Which is going to create carbocations. Okay, so for example, we could draw the positive charge here. Or okay, so electrophile attacks, creating a carbocation. Because of electron movement, we can have the positive charge in two different areas. Okay, now kinetic control versus thermodynamic control just has to do with what products are formed. Okay, so when you're talking about kinetic control, typically this occurs at very low temps or in a very short amount of time. And you end up with the less stable product. So, in this case, the less stable product, let's see. Sorry for all of the drawing.
No, it helps.
We would end up with substitution on adjacent carbons. This is referred to as a 1-2 addition. Which is considered less stable. We'll talk about why. If we have thermodynamic control, I'll write that first before I keep going. That's when you have high temps, a longer reaction time, and you create the more stable product, which show up here and here. Okay. So instead of it being a 1-2 addition, it's going to be a 1, 2, 3, 4 addition. 1, 4. Now this is considered the more stable. Can anybody think as to why this is more stable than this?
Because it's the internal.
Very good, Audra. Internal. Internal alkene versus, terminal is over here.
Oh, I remember this.
Terminal, internal. Okay? I know I did a lot of drawing. You don't have to worry about drawing necessarily. If anything, he could give you the final product and he might just say, if a 1-2 addition were to take place, point to the carbons that would be involved in that.
Okay.
So, assuming it would probably look very similar to this, you would want the carbons right next to each other. Okay, if it's a 1-4 addition, it's going to be the carbons on each end.
And so, those are always going to be on carbons that are singly bonding. Okay.
Exactly. Does everybody feel like they understand kinetic control versus thermodynamic control?
I get that. I understand that. Can we go back to their first original drawing, like that first one you have on the top?
Yep.
Where technically both of the double bonds are terminal, technically.
Sure.
And then what happens to get us to our two possible products?
Yeah, so I didn't really write that. So because it's electron rich, this can be attacked by an electrophile.
Okay.
When it's attacked by an electrophile, it creates carbocations. So this is just attacked by some electrophile, could be anything, and we would end up with these
And
two
that's
options.
kind of random, like it's nothing like the substitution elimination where it can only attack.
Right. In this case, we
Topside,
have
backside.
we have multiple areas where addition or attacks can be made. So
Okay.
you wouldn't have to worry about if it's stereospecific or anything like that.
Okay, so it's random to which products you have, but if you have a terminal product, terminal product, you get resulted in the 1-2 addition, which is kinetic
Kinetic control.
kinetic. But if it results in a internal
Mhm.
double bond, then you get the thermodynamic.
Right. You can almost think of it. So these, this type of environment
Mm-hmm.
leads to this product.
Okay.
this type of environment leads to this product.
Okay, that
Yeah, I
makes
could
sense.
definitely
Okay.
see him like just
That's-
asking broad questions like that.
Exactly, yeah. A lot of the fill in the blank. I think more fill in the blank can come from this than drawing or anything like that.
Yeah.
Okay?
He's gonna ask something like, "Oh, in a high temperature, what result? What do you
Exactly. And technically, if you leave this, after it's formed, if you leave this, this will eventually be formed. If you give it enough time, equilibrially speaking, it will,
get?" Okay.
He's like over a long period.
and it's more stable.
So even if you don't get the high temps,
Yes.
okay,
That's like if you leave it for a long enough
you
time.
just leave it long enough, it'll happen.
Okay. All right. Last thing we can probably cover from this chapter. There are more things, but I think these are kind of the big separate ideas. A lot of it is very, I think, repetitive. But all right. So Diels-Alder is a type of reaction that uses conjugated dienes. And for those of you that haven't been here before or haven't watched the videos, if you're concerned about what to know about a reaction, a good place to start is the name, if it has a name, the reactants, and the final product or the purpose for the reaction. Like, why are we doing this reaction?
You said that the Diels-Alder uses conjugated dienes.
Yes. So here's our conjugated diene. And it reacts with either an alkene or an alkyne. The example used in Dr. Cosper's notes is an alkene, so I'm just going to... Okay, so we have our conjugated diene and our alkene. Okay, and this is our final product. So you can kind of see how this bonds together. So essentially, you have electrons kind of moving to make this work. So you have electrons from here going to make a bond. Electrons from here going to do the double bond. Electrons from here going to make a bond. This is very similar to the last section, which talks about electrocyclic reactions. The only difference is electrocyclic is one molecule, and it closes and it makes a ring. This is made from combining two different molecules. So Diels-Alder is a little bit different. But your final product in this is called a Cyclo Adduct. This reaction is concerted, and it's stereospecific.
Now you could take any conjugated diene and any alkene to form a Cyclo Adduct, essentially.
I'm not sure if there are exceptions to that rule, but,
sure there
but
is.
my understanding is yes, you could probably do this. And also alkynes can technically be used as well. So an alkyne instead of an alkene. I'm assuming there you would still retain a double bond, but don't quote me on that. Okay. All right. So again, that's kind of the big things from chapter 14. There definitely are other things. I wouldn't say that that's all you have to study. Okay. Any questions over what we went over or anything that you wanted to talk about from chapter 14 that I didn't talk about? How are we doing on time? Still have half an hour. Is there another chapter?
He said there would be hold on, 16 questions from chapter 2 and 17 questions from chapter 9.
Chapter
We did
9.
9. No, we didn't.
No, we just
did
talked.
6 and 7 and 14.
2 I think I can handle so well. I would rather do 9.
I'd rather go over 9.
Okay, is that fine with everybody else?
Yeah. That's all right.
It's
Okay.
fine.
It's early.
I took a picture of it if anyone.
Oh, how many questions round what?
She has
Yeah,
it
I
in
have
there.
it.
Oh, okay, I'm so sorry.
Right here. The sheet game.
Chapter 2, because I'm freaking out. Chapter 2 is acids and bases.
Oh,
So
yeah.
much abuse.
I was fine on that. I just kept mixing up the K's, and I think I finally. Big K equals negative. Little K equals positive.
Okay.
Negative
So-
K equals
I do want to just jump back to chapter 8 really quick, just because it's important to understand how alcohols are ionized. That's kind of a big part of this chapter.
Thank you. We're talking about chapter 9, correct?
Yes. 8 and 9.
I'm just going to talk about one thing from chapter 8. So it's going to be most of the chapter. Okay. So we can have.
I did not write this out for
Sorry.
No, it's okay. Okay, next you let me borrow a pencil. Otherwise you would have heard lots of swearing. Not at you in particular, at myself.
I think I'm going to take
That was
sure when
misleading.
you're done.
Well, I'm gonna write like ion names and stuff, so it might make sense to have that on there. Okay, so alcohols are amphoteric. Okay, you should know that term. That means that they can act as acids and bases. Okay, so when alcohols are deprotonated, so when the hydrogen ion is removed, we end up with a negative ion called an alkoxide. Okay. On the opposite side, if we protonate the alcohol group, we end up with a positive ion referred to as an alkyl oxonium ion. It's easy to get them confused. I don't know how great you guys are with your ions, but if you remember from Chem 2, regular chemistry 2, there is an OH negative ion, which is referred to as hydroxide. And NH4 plus ammonium. I don't know if that helps you remember. So same charge, same kind of ending in the name. If it's more complicated.
Positive charge is like a neum, where
Yeah.
negative is an I.
Yeah. Yes.
Could you define alkyl and that one and the alcohol side?
So the definition just has to do with what, like, the definition is this drawing, in a
Oh,
sense.
okay.
Yep. So
It's like
it's an alkyl group with a positively charged oxygen, which has to do with just having an extra hydrogen.
Oh yeah, because you added the positive
Exactly.
hydrogen and then
you
took away
protonate
the
it.
hydrogen.
And then this one you
Alkoxide
deprotonate.
And that's why that one's
deprotonated.
negative.
Alkoxide is negative.
Yes,
And the other one is
because you removed a hydrogen. Hi.
A student came in with like signed papers for Brenda.
Okay.
Can I tell her? Can she leave them with you?
Yes, but so there should be two forms together. I just need the white one. So if there's a yellow or a pink one, give her the yellow and pink one. Just keep the white ones in a stack.
Got
it. Okay, so this is really the piece from chapter 8 that you need to kind of carry into chapter 9. Okay, so there are some reactions that have to do with like how you can make this. Okay, so you can react it with a base, a strong base. That's kind of the way that they talk about in chapter 8. But you can also react it with alkali metals.
So in other words, you can deprotonate an alcohol using a strong base or an alkali metal.
Yes. Now, when we're talking about the speed of this reaction, like how fast does this take place, it has to do with how many carbon groups you have around this carbon. So,
So whether it's a primary, secondary, or tertiary carbon.
You got it. I was going to test you guys by asking you which one was which, but you already got it.
Sorry.
All right, no, it's okay. So primary alcohol because there's only one carbon attached. Secondary because there's 2 attached. Tertiary because there's 3 attached. So the more attached, like alkyl groups you have attached, the longer this is going to take.
But
Okay?
it still happens.
It still happens, but
Okay.
the longer it will take. So as we go to less and less carbon groups, we have more reactivity, which just means faster. Okay? So methanol, 1 carbon, nothing else attached, is going to do this the fastest, and it's going to react most readily. Okay? That has to do with steric hindrance. The more carbon groups you have, the more steric hindrance you have.
And then just a quick reminder for me, the steric hindrance is it any like bulky groups or is it specifically the methyl groups?
Any big groups,
Any
but
big group,
you're going
any
to see a
group
lot
of
of carbon
molecule.
groups. The methyl groups are pretty big because
So
the 3
anything that's
hydrogens.
not hydrogen.
Yeah, I can't make that overgeneralization, but yes. Most of the time, yes. Okay. Are people okay with this? All right.
I'm gonna take a picture. before
Okay,
you
yeah,
use
yeah,
it.
absolutely.
Sorry.
I am going to talk about Alkyl Oxonium next, so. Everybody got their picture? Okay. Oops. Okay. All right. So when we're talking about SN2, E2, all of those guys, we talked about alkyl halides. That's what chapter 6 and 7 talked about. But you can have other leaving groups. It doesn't have to be a halogen. So when we're talking about alcohols, this OH group is actually a poor leaving group. Okay? However, the alkyl oxonium, or the H2O molecule, is a good leaving group. So if we want to react an alcohol in an SN1 reaction, we need to first convert it to an alkyl oxonium ion. So you'll see in a lot of these diagrams, there's kind of always that first step where you have an alcohol, and then all of a sudden you have a positive ion. That's just making the good leaving group. So you're going to see that a lot in this chapter. The same rules still apply. So if you think back to the chart that we just did for chapter 6 and 7, when we had SN2, we had primary alkyl halide, right? Same thing would apply for alkyl oxonium ions. We would want a primary alcohol for SN2 reactions. Okay, and then technically secondary or tertiary would work for SN1, E1, but tertiary is best. But so if we had a secondary alcohol, we would turn that into an alkyl oxonium ion, and then we could run it through either one of these reactions. The main takeaway from this is don't get so blind, like don't put your blinders on and forget that you can have other leaving groups other than halogens. And the same rules still apply. You don't want a big bulky, a big bulky molecule for an SN2 reaction because of steric hindrance. It doesn't matter if it's an alkyl halide or if it's an alkyl oxonium ion. The same rules still apply. Okay. Okay.
So I could essentially just replace the word alkyl halide with alkyl oxonium,
Yep.
and everything would still be the same.
Same.
Okay.
Okay. Let's see here. I think that's really it with this, but I'll leave it up there. Okay, so there are a couple different reactions. So esterification Williamson ether. And there's like an intermolecular Williamson ether. There are a couple other ones that are mentioned here, but these are really the ones that I think you're going to see the most questions on. I did just want to kind of talk about, because even though it's reactions of alcohols, there's other just like concepts that you probably should know. So carbocation rearrangements, you can have alkyl shifts or hydride shifts. Did he do one of those on your quiz?
Yeah,
He did. Okay. Maybe we
He
can
did
use
something
that
like that.
example if somebody has it.
I think he did a shift.
What
Yeah,
quiz?
there was a shift question.
No.
Chapter 9.
If not, we can talk about the example in the notes. I just thought it would make more sense doing it from the quiz.
I actually have a question on number 2 if you want.
Oh, okay. We can take this. Number 2, you said?
Yeah.
Okay. Okay. So this is unrelated. Okay. So it says here, molecule A below is 1,000 times more acidic than its alkane alcohol analog B. I don't see. That's confusing. This is due to what effect?
Oh,
Inductive.
yeah.
I'm confused. Where is B? Or are you just supposed to know alkane analog? Okay. So I think what he just means by alkane analog. The wording in that is a little bit weird, but so here we have essentially a haloalkane, right? We have 3 halogens attached. Here we have just an alkane, so no other substituents. So again, let me read it again. So this is 1,000 times more acidic than this. This is due to what effect? And then a hint is electronegativity makes it happen.
No, I got that one wrong.
It was
Oh,
the
is it
inductive,
inductive?
right?
Inductive
Yeah.
effect,
I
exactly.
just haven't memorized the clearly.
So the inductive effect is twofold, okay? It has to do with having electronegative groups. So the more electronegative groups you have, the more acidic that's going to be. And it's also distance between groups, like the electronegative groups, and the alcohol group. So another example of how he could ask this question. So these 2 molecules have the same number of halogens, but this one has many more carbons in between. So this one would still be more acidic because the electronegative or inductive atoms are very close to that alcohol. Okay? Doesn't sound like there was a hydride shift on the quiz. So I'll just kind of go over it on the board. Do you need me to keep this up, or is everybody okay?
Can I just ask a quick question out loud?
Yep.
That's unrelated.
Yep.
It says, which is the most stable free radical type? And I put chlorine, which is wrong. So,
There was a one where we had to draw a hydride shift,
Oh, there was.
if you want to.
But can I just see the
yeah,
wording?
it's everywhere.
I'm sorry, which one?
39.
39, sorry. I said 41, I was like, that's not orbital hybridization. Most stable free radical type, or are they all the same as far as stability is concerned?
I just don't remember what he said. I don't know if someone else says
Free
it.
radical types.
Is this the same chapter too?
It's the midterm. It's
Oh,
only 39. Yeah.
Yeah, so it's the one that's going to be tertiary. No,
I'm
it's tertiary,
tempted
tertiary.
to wonder if he's talking about. So, my first instinct, if he's talking about halogen free radicals, it would be it could be bromine, but I'm tempted to think this might be tertiary.
It is
39.
tertiary, apparently.
Is it?
Which is
Yes, on the
most
midterm. So I think he could have said like carbon free radical, but he just says free radical. So I'm tempted. Yeah, so tertiary is
Okay.
what. I think if they had carbon in there, it would have been clear. Okay. Oh, good. I think this is one actually exactly from the notes, so that's helpful. Okay. Thank you, Audra. So, we've talked about the most stable carbocation, okay? The cool thing about these molecules, though, is even if you form something that's not necessarily the most stable, the molecule can rearrange itself to make the most stable carbocation. Now, this can take place by either switching places with a hydrogen or switching places with an alkyl group, okay? So, can somebody tell me if this is a primary, secondary, or tertiary carbocation?
secondary.
Secondary. We have one carbon here, one carbon here. So we know that that's not the most stable. Tertiary is the most stable. So we need to switch places, switch places between the positive sign and one of the hydrogens. So if we were to move it this way, what will this be? Primary, secondary, or tertiary?
Primary.
Primary. Is that more stable or least stable?
Least stable.
Least stable, exactly. So, we wouldn't want to do that. However, if we move it this way, I bet it's primary, secondary, or tertiary.
Tertiary.
Okay? So, I should have looked at the question a little bit more closely. I'm sorry. Did he just want you to draw?
Yeah.
Yeah, he
The
just wants
shift.
you to draw it.
Okay, so you're just looking to find the carbon with 3 carbons attached to it. Now you can do an alkyl shift, which is just switching places with a carbon group, or a hydride shift. It looks identical.
Now, if we had started out with the primary, can we shift it down 2 hydrogens to make it a tertiary, or can you only move it over 1 for a hydride shift?
Oh, I see what you're saying. So
If the example he'd given was
yeah,
was at the primary carbon.
like
Like all the way through.
This?
Yeah.
Yeah, if that was like that, can you move it down to make it into a tertiary?
so technically speaking, this probably wouldn't form. It wouldn't be very likely that it would form at all, primary.
Oh, okay.
And I don't think you have to worry about him giving you that situation just because it would be pretty rare.
Yeah,
But I don't think that would really happen. And when I've seen it, it's only been shifting with something that's adjacent to it.
Okay.
So not moving to the other side, but I'm not sure
If it actually
what the actual limit is on that.
And then if it was gonna change places with a methyl group, what's that called? Is that
That's an alkyl shift.
alkyl? Okay.
Yep.
Can't pronounce it.
No, it's okay.
Hydride and alkyl shift.
Yep. Looks identical, just moving different things. Okay.
Well, so just sorry,
That's okay.
for an example for the alkyl shift, if on our tertiary carbon, if it was another methyl group,
So if okay, so something like this.
yeah, it just adjacent.
Yep.
Shift. Change spot.
So it's just an alpha group instead of a hydrogen.
Okay.
Okay.
Identical in every other way.
Mhm.
Okay. Some vocab terms you should know. So, crown ethers, cryptans, protecting groups. Functional groups you should know. Ethers, thiols and sulfides. This one, probably the least of those. Definitely no ethers, definitely no thiols. If you have a chance, look at sulfides. Those are really the big ticket items. Is there anyone in particular that you would want me to cover?
Files.
Thiols? Okay.
Okay.
So with this one, you don't have to worry about naming, which is nice. Okay? But you should be able to recognize them. In the past, I don't know if this is going to continue, there are several questions where you have to identify functional groups. Okay? So just be able to identify these. So a thiol is an alcohol analog. Okay? So we know that alcohols are this. Okay? Sulfur is an analog of oxygen because it's right below it on the periodic table. So it's going to react very similarly. Some things you should know about thiols. You should know some of their physical properties, okay? So with boiling points. Which has a higher boiling point? Oxygen or, sorry, not oxygen. An alcohol or a thiol?
Thiol?
Why?
It's sulfur, which is a bigger molecule. I think I'm going off base now.
That's right. At least you offered. What type of intermolecular attraction can alcohols make? What are the 3 types of intermolecular attractions?
Oh gosh.
You mean like bonding?
Like
So,
covalent or ionic? Or?
no, so that's bonding. So I'm talking like van der Waals or London forces.
Dipole.
There we go. There we
Oh,
go.
I wanted to say it before. No.
I know, I was like, sorry.
And what's the last one? It's a type of dipole, very, very strong. Hydrogen bonding. Okay. This is in order of increasing strength.
So hydrogen being the strongest, London being the weakest.
Yes.
Okay.
So to understand boiling points, you really have to understand the attractive forces that keep them together. The stronger the attractive force, the more energy you have to put in to separate those molecules. Okay? So, London are the only type of attraction that nonpolar molecules can make. So when you're thinking of alkanes, right? Anything that's just carbons and hydrogens, that's why they have very, very low boiling points and are gaseous. Dipole is when you get into polar molecules. Okay, so haloalkanes. Hydrogen bonding is a type of dipole, but it only occurs when you have nitrogen, oxygen, or fluorine bonded to a hydrogen. Water is a great example of this. It can actually make 2 hydrogen bonds, which is why it has an insanely high boiling point for its size. So back to our initial question. What type of intermolecular attraction can alcohols have?
Dipole. Or
Hydrogen.
alcohol is hydrogen, sorry.
No, that's okay. Specifically hydrogen bonding, exactly. What about thiols?
The dipole.
Dipole. So
Okay.
thiols have lower boiling points than alcohols.
Okay. And that would mean it has a higher melting point than alcohols too, right? They work inversely, or?
Sorry, no, I have to think.
Sorry.
No, it's okay. Melting point. So
I think you're right. I think so.
they would still have a lower melting point.
No, I think you're thinking about something we read
Yeah,
recently.
you're
on
thinking
the
about
quiz.
cis and trans,
Oh, yeah.
which was a very
Which
weird
is
concept.
opposite.
Yes. Okay, so lower boiling points than alcohols, but they actually are more acidic. Okay, those are 2 things you should know about thiols.
And then naming them is just.
You don't have to worry about that. He's not going to ask you.
Okay.
And typically when you are naming thiols, you use common names, not IUPAC, which I think is one of the reasons why he
Doesn't even do it.
isn't concerned about it. Okay. Ethers, on the other hand, you do need to know how to name.
Ethers is with the oxygen in the center too, are
Yep.
Yes.
So you just name like the alkyl groups on either side.
Yep. Does anybody need to review that, or are we all feeling comfortable with that?
Well, it'll just be like a methyl ethyl ether.
Well, it would
Or-
be ethyl methyl because you want to
Yes.
put them in alphabetical order. But
Yes.
yes, you are on the right line. Yeah.
Okay. Okay, yeah.
Okay.
They're like oxycyclo.
So that's
Yes.
cyclic
yeah.
ether. Yep.
Yeah.
Yep. So
Those throw me off.
Not a fan of those.
they're not as bad as they might appear. Okay. So when you're naming cyclic ethers, the first thing you do is you name the cycloalkane name. So if this didn't have an oxygen in it, how would you name it?
Pentane.
Pentane. Cyclopentane.
Cyclopentane.
Once you have that, you just add oxa in the front.
Why?
I know. Ethers are a vacation compared to other naming other molecules.
He had one where the oxygen was replaced with a sulfur, and I got that wrong and actually never actually figured out what the name was.
Do you have it?
Not on me,
I
no.
do the structure first.
Yeah, the first one, not the
Yeah, I
second
just
one.
know that I have.
What was
it
that?
So that's
Does that
not
sound that way?
hexane.
So it'd be 1, 2, 3, 4, 5. Hexane.
That wasn't on the
Look
first.
up
Oh,
this.
okay.
Yeah.
I
So
thought
just
it was
just
the
count
name.
the points. Yep.
First
Yeah.
one we only
Don't.
had-
Those aren't carbons.
We only had
I thought it would've been.
oxycyclopentane on that one.
Oh, I'm sorry, he replaced it with nitrogen, and it was the
Oh.
azacyclo.
As a cyclohexane.
Yeah.
You wanna have?
That's.
I think
Yeah.
that's just one he's just gonna put on so we know what in this quiz.
Yeah. It's really just.
And
So
he
that
did
one's a tough one.
He
That was a
did
tough
say
one.
he's not going to make us just pull the names out of thin air. He's going to give us the structure
Matching.
and the name and just do
Yeah.
the matching.
Yeah.
Yeah.
So this one is easy to kind of register with your oxygen. But you'll notice that a lot of nitrogen-containing groups have aza, azide, azo. So that's just, I know it's not as nice as oxa, but that's just one thing. And again, he's going to give you that.
Yeah.
So I would just link that in your brain.
Okay.
It's not something that you necessarily have to memorize, but you should just notice it.
Very much messed up on
You don't have to worry about naming sulfides. Technically, again, some of these functional groups are up for grabs that I didn't necessarily put on there, but I just don't think it's I don't think it's going to be a main focus. I don't think that you should put a lot of time studying into it.
Okay.
But if you're feeling comfortable with the big things, then you can get into the nitty gritty on some of these. But I wouldn't necessarily say you got to go study sulfoxides and know how to draw a sulfoxide. I don't think that's going to be a big
For
focus.
the sulfides, it's similar to thiol, where with the
It's
But it
basically
does
it's
the ether.
it's the
The
ether
sulfur
dialect.
ether,
Yep,
yeah.
exactly. Ether analog.
okay.
Let's see what else. For Williamson ether, other than knowing the name and the reactants in the product, you should know that it's SN2. That's written right in the notes, though, so that should be helpful. Are we doing on time? Is that about it?
I think we're
About
done.
Okay. Any other last minute questions?
I'll have some for you on Monday.
Okay, yeah, again, so Monday, 8 to 10. And I think I sent it to Dr. Fred correctly, but another email might have gone out with a different time. But Tuesday, if you're not taking it until Wednesday, I will hold a session from 2 to 4.
Okay.
So 8 to 10 Monday, 2 to 4 on Tuesday. Okay?